So yeah, welcome everyone. Thanks for joining us. My name is Nicholas Lane. We have got a jam-packed event for you for November. You'll see here with the screens, we've got a number of external folks here who've got some great talks to give us. Let me give you a rundown of the agenda for November. So what we have is we're going to kick things off with a flower update, just a very short summary of some of the most exciting things that happened in flower in the last 30 days. I'll try to make it brief though, because we've got three killer talks, really amazing talks here. We've got Mohammed. He is a member of Flower Labs. He's going to be talking to us about uh, flower intelligence, which is an approach for executing AI models locally that are backed by confidential remote compute. He's going to be sharing with us why this is amazing, how you can get involved, how you can start using it yourselves, giving you some updates on that. Then for our second talk, we have Chong Wang and a number of his teammates. Their names are Sahil, Alexander, Oscar, and Kai. I think I got them all just then. They are from the University of Toronto, primarily, and they're here to talk to us about their winning submission to a hackathon that recently took place. They built on top of Flower, but really put together a really amazing framework for those people working in healthcare to make it nice and accessible, which is something that we're really passionate about at Flower. So it's great to have them with us. And then we're going to close things off with a talk from a student at the University of Cambridge. G, he has worked on this system called Stratos FL. Yeah, it's a really solid piece of technical work. I'm super excited to see how it's working and what he can share with us. It's in the FL space, so it'll be something that many of you will be really keen on seeing. Okay, so let's look at the flower updates before we get to those great talks. First thing I want to share is this week we released flower 1.23. And so this is another great step forward. You'll find it's jam-packed with a lot of different capabilities that people have been really looking for. One thing I really want to highlight is that it now includes a migration guide from OpenFL to Flower. We're delighted recently to have Patrick Foley, formerly of Intel. He was one of the leading architects of the OpenFL framework as one of the sort of primary things he was doing at Intel. He's joined Flower Labs, and now he's helping us main continuity of offering for OpenFL users by helping them move to Flower. In terms of exciting examples, if you're into brand new things like quantum, we have an example that's been contributed by a user of Flower that combines quantum and federated learning. So pretty radical ideas smashing together that you can check it out and see what you can build on top of. Now, in terms of nuts and bolts of how the framework works, we have the supernode lifecycle has been completely refactored in this version. And you can use the CLI now to do dynamic management of these supernodes. So that's what we sort of have for you as sort of highlights of this new version. You might remember maybe as far back as 6 weeks ago, we had a big hackathon in Stanford. We're back again, this time in Berlin. We're going to have a hackathon with Excelsius, which is another company working in the sort of decentralized space. We're going to be based in the Einstein Center in Berlin. And this hackathon is going to be, again, all about enabling people to build various kinds of federated and decentralized methods using the Flower framework and combining it with some of the software components and sort of quite important levers that Excelsius also provides. So this is going to be exciting stuff. It's happening in about 10 days, roughly speaking, from now. So if you're in Europe, head over to Berlin. And then lastly, I wanted to mention an event we ran last week. It was the first time that we did a deep dive into one of the verticals that's so important for federated learning. And we did a country-specific event for the UK because there's as people realize, there's a lot of um, country to country variation. And so the UK has been putting a lot of effort into building responsible forms of AI to support health and life sciences. Um, we've been working with a lot of folks in that country. And so we want to run an event to kind of bring together the people we've been working with, bring together other folks who are curious about how you might use federated and pets and other technologies. And so we had more than 10 different talks. Some of them were from folks from Flower, other were from folks such as academic institutions or organizations in this area that we all came together to share, war stories, best practices, what works, primarily when you're using Flower to build federated approaches in this domain. It was also an event that we want to bring people together to launch an accelerate program just for this, the UK specifically, so that we can tailor make it to the types of systems, the fact that the NHS is a nationalized health service, so we can really sort of start to standardize some of the things that we're offering people. And so we can imagine that although this was a UK specific event, we plan to learn from this, see how we can use open source to accelerate adoption of responsible, types of AI in the health domain, and then generalize it across the other countries. But for this particular program, we offered folks 3 different ways that we can help out. The first of these was a new type of academic grant where you could have access as an academic or as a research leaning institution for many of the types of systems you want to build. We're going to offer you the capability of using SuperGrid, which is our offering that we launched back in flower.ai Day that enables it to be even easier to build safe federations, even around the world or around the country. We're going to offer that for free for people in these academic or research leaning institutions in the form of an academic grant that you can apply for. Second, there was this initiative where we're offering awards, financial awards for people who can document and make modifications to the Flower framework to ensure that it's compatible with the large variety of HPC. So this is cloud, TEE. So this is hardware supported, secure and safe environments to run and use sensitive data. And then also SDEs, which is another variant of this theme. Within the UK, there's a lot of variations between the different software and hardware that these types of capabilities are offered. And so then this second program that you see here is all about offering financial awards to people who want to show that Flower is compatible with one or more of these systems. And then finally, we know that a lot of people are looking to get larger and larger research grants in this space, and we want to help out. And so this third part of this program is to simplify the way that we can help you with the grant writing process by offering you in-kind support for when you're trying to build a federated consortium or a federated type of research, letters of support when you're submitting these grants. Again, this is obviously targeting academic scenarios and research labs who are seeking public funding to build demonstrators of this kind. So again, letters of support, in-kind contributions that could support things like technical support when you're building on top of Flower to build these demonstrators. So these are 3 different avenues of this program. Obviously, I'm just giving you a sort of very high-level overview. If you are interested, you should feel free to use this QR code to have a look at these programs in more detail, because we're really here to help everyone working in the life sciences and healthcare space turn what could be a 5 to 10 year mission into more like a 2 to 3 year approach to accelerating AI adoption of this kind to benefit everyone. That's what we want to see happen. So that is a fairly rapid overview of things we've done in the last 30 days towards open source adoption of federated learning. It brings me to the first speaker for Flower Monthly, and that is Mohammed Nazari. You would have seen him in many other Flower Labs events. He is one of our leading experts in various kinds of security and privacy and has how that interacts with federated. And he's here to talk to us about flower intelligence and see, what are the updates in that direction. So I'm going to hand over to Mohammed and see what he has to share with us today.
Great. Hi, everyone. I'm Mohammed. I'm a research scientist at Flower Labs. And today I'm going to talk about flower intelligence, one of the recent projects at Flower Labs. All right. I would like to say that the decentralized AI actually leverages a two-phase approach, and it's the training phase and then the inference phase. And I think all the people in this presentation, they're familiar with decentralized and federated learning, where how different entities actually they train a model without sharing data. And essentially, we have different entities with some local data, and then we have a centralized server. The server starts with some random model, communicates that model to those clients. They do the local training, and then they send back the updated models to the server, and the server performs some kind of aggregation and then communicates back the updated model to the entities, and we continue this process until we achieve a converged model. And that is the training and federated learning part. But now, once we have the converged model, actually comes the next challenge. And the challenge is how do we use the model in practice in a safe, efficient, and scalable way? Because federated learning itself actually resolves some issue and risk for us, where we can avoid any direct access to the local data. And with some privacy enhancing technologies applied, we can make the whole process of federated learning secure and private. And once we have the model, actually, we need to do the inference, but the inference itself comes with some risks. And generally, there are two approaches for performing the inference and deploying a model in a decentralized setting. One is cloud-only inference, and the other is edge-only inference. But the thing is that each of these approaches, they come with some challenges. For example, in cloud inference challenge, we can have the privacy and regulatory constraints because data actually leaves the client or the entity, and that can cause a potential violation of different laws like HIPAA, GDPR, and etc. The other issue is that we might have latency and reliability because the cloud inference itself introduces a latency, and also those clients and the entities, they need the connection to internet. The other thing is actually the cost and the scalability. The cloud compute itself it has some costs, and those costs can grow with the usage, and that usage could be the per token, per image, or other metrics pricing. And the last thing is the bandwidth impact, because suppose in a decentralized setting, the clients, they constantly uploading large images for inference or any other type of data to the cloud, and that actually consumes bandwidth and energy. That is about the cloud inference challenges. But on the other side, local only inference also comes with some challenges. For example, the first and the obvious one is the limited computer memory, because there are some certain like high complexity models that they need like powerful devices, and some devices they don't have that capacity. The other thing is the update and the maintenance, because when we make the AI models live on the devices and the entities, we also need to update them. And if we only do a local inference and actually cut the communication to the devices, updating them is becoming a challenge itself. And the last one is the collaboration and the federated improvement gaps, because those local entities and devices, they also need to provide some performance feedback into a centralized system so we can improve the model and deploy an updated model to those clients. So the thing is that actually neither solution is sufficient on its own. We cannot rely only on cloud inference or only on local inference. And that's actually where we have introduced Flower Intelligence at Flower Labs. It's an open source on-device AI with confidential remote compute. So Flower Intelligence prioritizes on-device inference for speed, privacy, and offline use. But as I mentioned, there are cases that the device is not powerful enough to run the workload. And in those cases where we need the extra power, Flower Confidential Remote Compute actually steps in as a seamless private extension of the device. And Flower Confidential Remote Compute actually doesn't compromise privacy, security, or performance. So with Flower Intelligence, we can have a hybrid approach of local inference and cloud inference. Flower Intelligence has some SDKs, and they're in TypeScript, JavaScript, Kotlin, and Swift. And you can easily actually install one of those SDKs, and you just specify one of the models, which I'll list later in the presentation. And then you just need to pass your prompts. And in this way, actually, this pulls the model on the device and then performs the inference on the device. So this is for performing the local inference in Flower Intelligence. But if extra power is required, then that call would be redirected to the Flower Confidential Remote Compute, or CRC in short. So CRC provides some data protection. It provides data protection at rest, in transit, and in use. So in CRC, actually, no private information is stored. The only information that we save is regarding the usage, and that's for the billing purpose. In transit, actually, all the communications are end-to-end encrypted, where the keys actually are derived from the hardware using T and confidential compute. And also, it provides the data protection in use. And I'll explain how that works. Flower CRC actually utilizes T's and the NVIDIA H100 GPU in confidential computing mode. We actually would put the LLM inside the GPU, and then the execution code resides in the CPU, and the communication between the CPU and GPU is also encrypted. And then the whole workflow is that the user actually gets a key from Flower CRC. It uses the key to encrypt the prompt. It sends the encrypted prompt to Flower CRC, and the prompt only gets decrypted inside the TE using the private key. So even we at the Flower CRC side, we cannot access the raw prompt. And then it communicates the prompt to the GPU for inference, gets the response again, encrypts the response, and then communicates back the response to the user. And it's only the user that can actually decrypt the response. So it provides a TE guarantee that uh, that's the hardware enforced memory isolation, integrity, and confidentiality. And as I mentioned, even against the host level access. And it also provides some attestation functionality for the user. So the clients, they can verify that the inference is running inside the trusted enclave. And they can check this before sending any prompt. And they also get the key through the attestation mechanism. So currently, these are the models that we support in Flower Intelligence. Obviously, those small models like Llama 3.21b that can, I mean, it depends on the device, but you can run that on your laptop probably using one of the SDKs that I mentioned. But for like bigger models like the Qwen 235b, obviously this cannot be loaded on the local device like the laptop. And for that, you need to call the confidential remote compute. But there are also some models in between that, depending on the case, you can either do local inference or use the confidential remote compute. So all the documentation for the Flower Intelligence are available. You can check it out using this link. And if you're interested about confidential remote compute, you can scan this QR code and then you register your interest, and then Flower Labs will contact you to provide you with the infrastructure for deploying the model that you want and helping you with the project. And that concludes my talk. Are there any questions?
Thank you, Mohammed. That's a great talk. I see there's one question on Slack. The question is, if they are building an app for a laptop, can they use this?
Yes, obviously. Actually, it depends on what language the app is developed in. But
Mm,
as I mentioned, we support different SDKs. So you just need to import that SDK in your project, and then you can do the inference part either locally or remotely using the confidential remote compute.
right, makes sense. Um, yeah, I don't see anything else. Okay, so great. Thank you, Mohammed. Great talk. It's a good example of how, we have a broader attention um, at Flower to enabling people with open source to build all kinds of privacy or decentralized forms of AI. So this one is an example of a federated inference in some sense. Yeah, so great. Thank you, Mohammed. Let me share my slides and we can move on to our next talk. So our next talk, I'm super excited to hear. Um, as you can see here, there's a large group here, all in Toronto, I suspect. These were the folks behind Guardin, I think. I don't know if I'm saying this right. Um, but they won this 2025 Toronto um, biohackathon kind of thing. And they did this by building a toolkit for FL, but more importantly, for people working in the healthcare domain, if I understand. So I'm eager to learn all about it. We have here Chong, but also, as I mentioned before, his colleagues, Sahil, Alexander, Oscar, and Kai. Plus, I hope I got everyone's names and everything. So over to them. I'm really curious to learn more about this and see what they've been up to. So thanks for joining us.
Hi, thanks. We'll just share the screen. Can you see the slides?
Yeah, it looks perfect.
Perfect. All right. Okay.
All right, so we are Guardin. This is our team name for the hackathon project. And so I'm Chong.
I'm Alex, third year undergrad at U of T in bioinformatics and computer science.
I'm Sahil. I'm a third year undergrad at U of T in computer science and quantum physics.
I'm also a third year undergrad. I'm doing data science and computer science.
And I'm Kai. I'm a undergrad computer science student as well.
Yeah, I forgot to mention, sorry, I forgot to introduce myself. I'm also a third year computer science student studying also studying bioinformatics. And
Yeah, we are presenting today from the beautiful city of Toronto. As you can see, here's a picture of our lovely front campus. And we're actually in the basement of a library that's a bit to the right of what's shown in the picture. And yeah, I just wanted to start off our talk with talking a bit about what we actually won, Toronto Bioinformatics Hackathon. It's a student-run hackathon, which for the larger Ontario, like the province of Ontario, the larger bioinformatics community, and it is the largest bioinformatics hackathon in Canada. To build Guardin, we had a 28-hour coding window, and there were 151 participants across 25 teams. Of the 25 teams, we won the first place prize with Guardin, and we are very excited to be able to talk about it with you guys today.
all right, so I would like to introduce why we built this project in the first place. So as we can see that AI in healthcare is really skyrocketed over the past few years, and there's a lot of publications for new models for screening and diagnostic purposes in healthcare. This is really good. However, in reality, there's a lot of issues with data. So this is actually our motivation for the project. Over the summer, I was working with Dr. Chow. She is a respirologist in Toronto General Hospital, and we were trying to train a model to detect restrictive lung disease based on only spirometry data. We first tried using UHN, which is the University Health Network's own pulmonary function test dataset. However, it is has a very small sample size. The data set is very biased towards restrictive cases, which resulted in a lot of generalization problem when we tried to run it in other colleagues' data from Montreal. So what we tried to do is we contacted this colleague in Montreal and we were like, can we share data so we can train a better model with more balanced data set? However, I didn't realize that in healthcare, there is an extensive process in terms of data sharing agreement. There's a ton of ethics approval, which can take months, even up to years. And to expand on the second point, there's more difficulties in sharing health data. First of all, health data is very sensitive. It has a lot of private patient information, which could cause the patients a lot of harm if the data is breached. It is also very large, namely videos, and can be really a hassle to transport between the different hospitals or data centers. And lastly, it is super difficult to anonymize. An attacker can easily identify a victim from a large database. An example of this was in the 90s, there was a genome-wide association study of many people to find genetic variations, typically like single nucleotide polymorphisms. It was open sourced. And in 2008, Homer and al. Published a paper that can find using weak correlation tests on these single nucleotide polymorphisms to identify whether a patient's DNA was in the data set. And this resulted in the National Institute of Health having to remove all of the data set because it has been compromised, as shown to be able to be compromised. And at the end of the summer, we all came together as a team and we decided to try to find a way to do this in a hackathon where we can solve the problem of the traditional ML being so centralized and so data-centric that all the data has to be pulled together. So we wanted to build a system that can train a model collectively using decentralized data sources, which is why.
And this is what brought us to Guardin, which is a platform for healthcare professionals to lead and contribute to federated learning projects. And so just because we said that it just wasn't feasible to move all the data in a safe and secure way to the computation, what instead we're going to do is we're just going to move the computation to the data. This is actually a quote from the Flower website. But so with the federated learning and using flower.ai. Oh, why is this went the wrong way? How do I? Sorry. There you go. And so just as a recap, right, the idea is that we're going to have one centralized server that's going to hold the actual model weights. And then all these little clients here in this picture, client 1 and 2, would both be hospitals, and these would have their own data sets. And instead of sending over the data over any kind of network where it could be compromised, we're just going to send over the weights. Is the button?
Oh, very good.
So then, yeah, so using federated learning, we're only sending the model weights over the network, which already heavily minimizes the potential exposure of information. Additionally, we're essentially training one model over all the data sets, which addresses the generalizability issue that Chong mentioned. So by combining a bunch of hospitals that could have slightly different data sets and more varied, we can end up training a global model which can generalize better. And then finally, we also implemented differential privacy on the server end. So by noising the weight slightly, this minimizes the risk of a reconstruction attack or the damage it could do. So to recap, like not only are we not sending the data over, we're only sending the weights. And then furthermore, we're noising the weight so that even if the weights get breached, we can bound the amount of information that an attacker could gain from these weights, which would make a reconstruction attack even less damaging.
Yeah, so now that our background has been well established, we're going to move on to talk about what we actually build. Guardin is an application which allows for medical professionals to easily collaborate on federated learning projects without actually having to code the models themselves or interact with them directly through code. We've developed both the Guardin desktop application, which is very easy to use, as we'll talk later during the presentation, and we are including a demo in the next few slides. We also built a Guardin server, which is an orchestrator that works with Kubernetes and flower.ai for starting and coordinating training. And as a proof of concept, we built two models, AlzheimerNet, which is a simple feed-forward neural network for predicting Alzheimer's disease given patient data, and TumorNet, a simple convolutional neural net for predicting classes of brain tumors from MRI scans. Throughout the rest of this presentation, we will be focusing on AlzheimerNet, but we built these two models just to show that the platform is really model agnostic. And no matter what model or what type of questions you want to answer in the healthcare space, the Guardin application allows you to do machine learning for it. And just to talk a little bit about our Alzheimer's dataset, it's quick from Kaggle, it's a hackathon, so we had to find something good. But it does have a lot of patient information, and it's very sensitive, obviously. You don't want to include medical history or to leak demographic details of patients. It's a simple binary classification that we made, whether or not a patient has an Alzheimer's diagnosis or not. And while the dataset is relatively small, we believe that it's a good proof of concept for expanding, and we have a very scalable architecture, as we will talk about in our demo and our tech stack.
Right. So now we're actually going to show just a quick demo of what Guardin looks like in practice. We're just going to open a video that we made. All right, so here is, here's what, where's my mouse here? Here's what Guardin looks like for a healthcare professional opening the application. Here's our demo. And so we can see, I'm just going to pause it a little bit to explain what's happening, but here this is what the dashboard looks like of the application. And so there's all these different models you could choose from, and it'll say like what kind of data set it needs. So here we're going to use the Alzheimer's predictor model, which needs a CSV. So if we click on it right here, we'll we'll go to a new page. One second, here we go. And so here, as you can see, it's very easy to do. We can actually just drag and drop it. So here's Alzheimer's disease data.csv. This sort of simplification, but this is what the hospital workers would see. So you would just take the CSV, drag and drop it in here. And then when we press upload data, now don't worry, the data is not going anywhere. What this is actually doing in this step is it's pulling a copy of the model from our registry, and it's just mounting this CSV to that container so that we have the training all set up. And so it's going to load, and then there we go. And as you can see, it's going to show us the output of the Dockerized model and the data mounting. So when we did this, you'll see in 1 second, we don't show it here, but there's actually 2 laptops at the same time doing this. So this is simulating 2 hospitals have now drag and dropped the data set into this box. And then the server, we've pressed start training on the server end. And as we're going to see, it's going to start showing us the output. This output isn't very important for a special. This is more for us to be able to see what's going on. And if we scroll down, we'll see that we've digested the outputs into a much more understandable graph for the users. So this is giving us real-time updates of the accuracy and the loss throughout different training rounds. This is of the global model. And so as we can see the accuracy increasing and the loss decreasing, which is good. And here we did it for 8 training rounds. And so in a second, we'll see that it looks like it's about converged, and we can press download model weights at the bottom, because at every step, the server will send out the copy of the global model. And so when we download it, we can just download it into an NPZ file that's zipped here. And yeah. Okay, so that we just showed, this is what it would look like, one federated training of the AlzheimerNet model. So it successfully worked, and we saved it. Now I'll go back to our presentation. All right. And this also shows then that we can reconstruct the model from those weights that I downloaded at the end of the video. So this just shows us how one hospital then would take this file, the weights, reconstruct the model, and then run it on their data set, and it'll present a report of how the model does. So this is the global model applied to one of the data sets. And so what we actually did for this project was we trained the AlzheimerNet model twice. Once centralized ML, which is the traditional way, where we had there's one data set and we trained the model on it. And then once Guardin, we federated it across 2 clients. And so by studying the curves of the loss and the accuracy, we noticed that the centralized ML model converges faster. It attains roughly 82% accuracy by round 4 of training, versus the Guardin model, the federated one, takes a little longer. So we can see the slope of the accuracy curve is a little lower. However, it ends up getting to the same accuracy by maybe around round 6 or 7 instead of the 4th round, but it ends up at the same accuracy, just needs more data to converge, which we noticed was consistent with the literature, which is that the federated learning can take a little longer or needs more data to converge. However, the privacy benefit that speeds up the acquisition of data, we think outweighs the cost of needing more data.
As you saw in the demo, we have a bunch of different models that we wrote training scripts for. And the way it works when you select which model you want to federate learning for on the front end is that it actually pulls one of those different images containing our training scripts for either the AlzheimerNet or I forget the name of the TumorNet model from our Docker registry, which then runs the Flower client and our PyTorch model and communicates with our Kubernetes hosted flower.ai control plane that coordinates all of the training between all the different clients. And when you actually interact with the app, it is directly communicating with the Docker container that's running locally to get things like the training progress and all the weight updates.
So our tech stack and our backend seems pretty complicated, but the entire appeal of our app is that it's super easy for healthcare professionals to use with little CS experience. So the way we accomplish this is for data uploading, we clearly just display the types of data files that our models will accept. And then once they're uploaded, if there's like some formatting issues in the data file, then we indicate that to the healthcare professional, like exactly what's going wrong. And then here we could also implement maybe some auto formatting to make the data uploading even more seamless. And then once they press the upload data button, we send a Docker command to retrieve the model weights and then begin training seamlessly. And then we get the Docker output from the server, which is pretty complicated itself. And then we parse it into something that's digestible for someone with very little CS experience. So our complicated Docker output turns into just accuracy and loss graphs, which are simple to read as if the green accuracy graph goes up, and the red loss graph goes down, then that means that the model training is going well. And then our app is super portable, like our Electron desktop app. Instead of using a web app, this allows us to ensure that there's no like intermediate server where we have to upload the data. Like everything can be happening, or the entire training process can happen locally, which mitigates any privacy concerns for hospitals because all the data like stays in the institution. And then because it can be built for any OS and then downloaded on GitHub, it removes all the hurdles for institutions to upload their data.
All right, and now just to end off our presentation, we'd like to talk about a few future developments that we want to see with the Guardin app in the future. First, we'd like to improve the metrics for many things. First, those being model quality. We want to include more than just, loss and accuracy. We want to include more model metrics and make those communicable with the actual healthcare professionals who are using the app. And one big issue with actually including federated learning projects in the real healthcare space is the fact that hospitals might not have incentive to actually share their data to a larger global community. So if we include incentives for contribution, as well as weighing contributions for data quality and data variability from many different sources, this will improve both the size of the data sets that we're actually getting from many different communities, and also the quality of the data set, improving generalizability of the predictions and improving the use of Guardin as a whole. Additionally, the next set of bullet points that I'd like to talk about are general improvements to the app itself. First off, we'd like to include guidelines for both model building in case people want to add models to the Guardin architecture, or pre-processing data, where you could have guidelines for pre-processing data before it's actually uploaded into the Guardin server to actually automate that process. We also have more analytics and progress for model training, as I was mentioning a bit before when I was talking about metrics for model quality. And as Sahil was mentioning before, we have the start of a dataset auto-formatting pipeline. But if we include the actual logic to take the files and auto-format them, that would make the process a lot more easier for healthcare professionals actually using the application.
Another thing we want to add to the model is non-IID detection, which is a big issue in healthcare. If you have different hospitals that are like consistently producing different results for one reason or another, like maybe the machines are different, we want to be able to detect this, at least detect it and ideally correct it on the server end without the client having to do anything. So we can do something like, for instance, dynamically switch strategies as needed. We can, right now we're just using federated average as a strategy, but we could have a case where, for instance, the server will detect batch effects occurring, and then we'll switch to like FedNova, for instance, which is an algorithm to mitigate non-IID-ness of the data.
And finally, we'd like to focus on model interpretability, which is a very important point in healthcare settings. Because if you take a prediction from a model and you have no explanation for why it's given that, it's going to be very hard to get healthcare professionals and patients to actually want to use the information that the model is using. One thing that we found in literature are Shapley additive explanation values, which, as cited in the paper that's cited below, have actually been cited in federated learning research in healthcare settings. What SHAP values basically are quickly is they provide a little bit of an explanation for the importance of specific features and why a model would, or what features a model is looking at in making a prediction. So if this data is, processed and made more clear to healthcare professionals and patients, it could also improve the interpretability of the app. And one final point that we'd like to talk about is that the fact that Chong mentioned that he was doing work at UHN with Dr. Chow. I am also doing research at the Princess Margaret Cancer Center at UHN, which is it's a set of hospitals in Toronto that includes the Toronto General Hospital and Toronto Western Hospital and other research centers, including the Princess Margaret Cancer Research Center. And using our connections at UHN, I am under Dr. Benjamin Hyde-Keynes. We are hoping to actually explore use of federated learning in these healthcare spaces.
See the citations, and thank you, and check out Guardin on GitHub.
Yeah, so that's the end of our presentation. Thank you so much for listening.
Amazing stuff, guys. Very cool. So yeah, if anyone wants to ask a quick question right now online, feel free to raise your hand if you're in the webinar. I'll keep my eye out. Oh, we do have a Oh, I see. We have a question, anonymous question. Question is, hey team, absolutely love this project and your roadmap. How long did it take you to build the app?
Uh,
It was a hackathon project. We had 28 hours to code. It took us about 14-ish, but we were doing model training too, and it took a while. Debugging took a bit too, but yeah, everything was able to fit within that 28-hour window.
we didn't get a lot of sleep though.
Yes, that is very true.
Yeah, I can imagine. Were you first time Flower users on that event?
Yeah.
Really? Wow, that's awesome. Far out.
Oscar
Um,
did a lot of reading before the
Yeah,
hackathon.
we did literature review to actually make sure that we had the points for next steps, what research has actually been done on federated learning in the healthcare space, that sort of thing.
Yeah.
awesome. Awesome. Let me take a look on Slack. A question is basically saying how can you change the model architecture, I guess, or even just model type? Um, yeah, I guess from the view that you showed, it wasn't so obvious about how
Oh,
you might change it.
yeah, basically, the way we did it, we basically just wrote a couple of models, and the idea is like since we have them on this registry, you can just click on whichever one you want. So,
This is not here. Go back to
it's back to the demo,
We'll start the
but you basically there's a lot of different buttons you can click, and then clicking on any one of them
Yeah.
here, if you click on this, it'll bring you to that next page for that model. So you can't see the mouse in this video, unfortunately, but then we clicked on Alzheimer's predictor, we clicked select Alzheimer's predictor, and then it brought it to that second page.
I see. So you pick discrete models where everything or everything is already predefined.
Yeah, so
Um,
we're hoping at some point people will contribute their own models to Guardin, and then they'll show up on that page.
oh, very interesting. That's cool. Yeah. Let me see. Oh, another question in the window. Yeah. There's so many windows. Oh no, we answered this already. Okay, fine. Good. Okay, well, I mean, that's cool. Amazing project, guys. Really impressive. I think everyone should check out Garden. It's amazing stuff.
Oh,
Great.
thank you so much
Yeah.
for the opportunity.
Thanks.
Yeah, thank you. Great. We will go now to our final talk. Okay. Okay, so the final talk of Flower Monthly for November is by a student of the University of Cambridge. Um, we have Horan or Samuel G. He is going to show us Strato FL. So it's more of a piece of sort of academic work in the direction of how do we make federated better. Really excited to see what he's done, the results, what he's found. And yeah, thank you so much for sharing it with the community today.
Thank you. Thank you very much for the invite. Let me share my screen now. So I'm going to share, I'm Samuel. I'm from Cambridge. I'm going to share today my dissertation work for my part two project that I did together with Javier, who is also one of the researcher in the Flower Lab. And the name is StratoFL, Federated Optimization for Heterogeneous Molecular Data. Oh. So here's a bit of the overview for the presentation today. Okay, gonna start off with motivations and aims, and then going through system overview of StratoFL. Next up, I'm gonna introduce a bit about the data sets I use for my project, as well as the what I call featureizers. Next up, I'm gonna talk about the different non-IID taxonomies and the partitioners I came up myself to simulate the realistic non-IID scenarios. After that, I'll introduce different aggregation algorithms I've used, and then at the end, I'll share about the evaluation part as well as the results and the conclusion at the very end. So first off, why federated? Why this work? Why? I think it's mainly because of the non-IE federated learning. Yeah, I think all the audiences they're probably already quite familiar with this because we know federated learning is very important, especially for privacy preserving machine learning. It enables when we have multiple organizations, such as hospitals, as the last project was talking about. We have hospitals, pharmaceutical labs, financial institutions. Federated learning allow them to collaboratively train a model without sharing their raw data, and then each client trains locally, and only the updates are being exchanged. And then I'll say the major issue is that in the real world, the data across different clients are really ID, independently identical and independently distributed, meaning they're not. So each institution might collect data from different populations using different experiments or under different experimental conditions. So this could be in my specific context of molecular machine learning, this non-idealness could appear in different forms, such as perhaps some labs specialize in small molecules, others in large compounds. Some assays record positive results, others mainly negative. And then so the label distribution, feature distribution, and the quantity of data differs between different institutions. So when this happens, you see that the global model trained across different clients tend to perform poorly compared to centralized case or the ID case. You see scenarios like slower conversions, you have biased updates, or large performance gap between different clients. So essentially, the model could become pretty unfair, where it's good on one of the clients, bad on the other clients. And then the research objective mainly is to uh, kind of look into the existing gap of federated learning research when we look at federated learning aggregation algorithm like FedAverage, FedProx. They have been only evaluated on toy data sets like MNIST, which are like artificially created partitions. So which makes it unclear how these different aggregation algorithms perform real life non-IDness. So the central question is, how could the existing aggregation strategies perform under the realistic non-ID molecular data, and how we can systematically benchmark them? And we see on the figure, this is a simple figure of how federated learning performs its overall pipeline. So the project aims are kind of four-folded. First one is to build the StratoFL, which is a molecular benchmarking frameworks containing different data sets, featureizers, partitioners, models, different strategies. By here, I mean aggregation strategies, and even differential privacy. And then second, to design those realistic non-ID partitioners and to evaluate aggregation strategies across these non-ID settings. I think one of the partitioners was also like already contributed to Flower, so you can actually access this from Flower's code. And then I wish to provide a reproducible evaluation on two molecular tasks, mainly aqueous solubility, as well as multi-assay activity classifications. And as an extension, I've integrated DP and to assess the privacy utility trade-offs between different aggregation algorithms. Oops, next slide. So here's a high-level diagram of the framework. On the left, I would say everything starts from YAML configuration files, which defines every component of an experiment, which datasets are we using, which featureizer are we using, partitioners are we using, and so on, which makes the kind of experiments very reproducible. And then each configuration loads in the molecular modular pipeline, which consists of 5 different key modules. You have data adapter that reads and pre-processes the data sets. And then we have featureizers, which I'm going to introduce in the later slides. We have partitioners that distribute data across different simulated clients. And we have the model aggregation strategy that defines the local training and aggregations. And finally, we have this optional differential privacy wrappers. Okay. So next up, I focus my project mainly on 2 sets of data sets. The first is aqueous solubility, which contains around 16K different molecules. They're all extracted from ChemBio, which is a large bioactivity database that's being widely used in drug discovery space. And then the second data set is what I call multi-assay activity. It's a much larger data sets with around 430 K molecules across 281 different tasks. And then you see the density is about 3%, which means a lot of the molecule task pairs are missing, which kind of reflects the true nature of bioassay data, which is highly sparse and incomplete and being distributed across different laboratories. Next up, we have featureizations. So once we have the data, next up is to extract feature from the data. So I think when we consider molecular machine learning, the difference between molecular machine learning and, let's say, traditional machine learning is that for traditional other set of machine learning, you have data sets already popularized with the feature. But most of the time when you're doing predictions on molecules, you actually featureize yourself because each molecules can be represented by this unique representation called Smiles representation that uniquely defines a molecule, saying, okay, what are the atoms in this molecules? What are the bonds in these molecules? So featureization basically converts this information we have into some fixed length vectored for training, for tabular data, for feed-forward neural network, for example. So for tabular representations, each molecules can be encoded into three different types of feature. You have descriptors, which are some physiochemical properties of the compounds, such as molecular weight, log P, topological polar surface area, which is kind of specific to the field, and you have fingerprint, which are binary vectors, also like kind of how specific to the field, how you featureize the data, and etc. So the resulting feature vectors will be fed into, let's say, in this scenario, a simple feed-forward neural network. And then we could see the visualizations here, how you transfer from the smile string to the feature vectors you have, and then feed into the model to get the predictions. A different form of featureization, which is kind of more interesting here, is what we have for the graph representation when we're using a graph neural network or message passing neural networks. The incentive here of using graph neural network is because we can think of each molecule as a graph with atoms as the node and bonds edge as the edge of the graph. Therefore, we could incorporate the graph neural network to do predictions of molecular properties like aqueous solubility in this case. And we can see it from the graph that shows an example of the featureizations we have. On the left, bottom left, we see a molecules, and then we have highlighted one of the atoms and one of the bonds and how we featureize them. Yeah. So this is the graph representation featureizations. So after featureizations, let's move on to non-ID that I briefly covered. So we need to define like what kind of non-IDness are there. This table kind of summarizes five main types of non-IDness and federated learning. We have feature distribution skew, where we have each client's input space differs, but the mapping from features to label is being consistent. Similarly, we have label distribution skew, where we have some clients seeing, I would say, the label proportion vary across different clients. Or in the case of aqueous solubility predictions, you might see one of the node having labels that's consistently centralized in a specific range. And you have same label, different features, same feature, different labels, and you have quantity skews. So here's the non-ID taxonomy. And then real-world federated learning usually involves multiple of these simultaneously. So in this project, I implemented partitioners targeting each of these types so that we can systematically explore their effect on the effect of non-IDness on the performance degradation, let's say. So in total, StratoFL introduced five main partitioners. We have the continuous partitioners, scaffold clustering, multitask pathological, multitask class ratio, and multitask Dirichlet partitioner. Collectively, these could cover the feature skew, label skew, and quantity skew, which I would say the diversity allows controlled, reproducible experiments on non-IDness. Due to time, I'm going to cover the two main partitioners, the continuous and scaffold clustering here. So the continuous partitioner is, I would say, the simplest partitioner, but also very general. So it introduced the skew by sorting sorting the molecules according to a continuous property, let's say molecular weight or solubility, and then assign continuous segment to different clients. And then the degree of non-idealness is being controlled by this parameter called strictness, which linearly blends the true property values with Gaussian noise. When strictness equals 0, we get IID split, which can be seen from the bottom left graph here. We have 5 different clients. Each of their distribution are pretty not IID. And then when you gradually increase the strictness, you can see increased non-IIDness being introduced. And then at the very end, when strictness equals 1.0, you see all the clients have very, very different distributions in terms when we think of this property. So that's the continuous partitioner. We also have scaffold clustering partitioners, which kind of uses this property of chemistry scaffold, which is the core structure of a molecules, and then do some steps of extracting the scaffold, computing the fingerprint, doing some PCA hierarchical clustering, and then mapping different clusters to clients. So here are 2 example partitioners for the projects. And then next up, we have different aggregation strategies. So how do we combine updates to from these diverse clients? We use fed average as the baseline, which simply average the model weights and weighted by dataset size. I've also experimented with fed prox, which adds the proximal term in the loss to keep local model close to global ones. I've also experimented with fed nova, scaffold, and flit. And this slide kind of gives an implementation overview of kind of having these different strategies in a unified framework. And then at the very end, I kind of summarize what are the main components and what are the actual components I need to implement for these specific strategies. Yep. And then this figure shows how these different strategies integrate within the Flower framework. Flower separates concerns into 3 layers. We have client, server, and strategies. So each aggregation method will plug in at the appropriate layer. For example, I could define a custom optimizer on the client or a new aggregation rule on the server. And then, yeah, this is basically the Flower architecture. And then some specific to the strategies I've implemented. Next up, we do the evaluation overview. So the evaluations aims to answer 4 core questions. Firstly, how much of the performance degrade when data becomes non-ID? Secondly, to look at which aggregation strategies can mitigate the degradations. Thirdly, to see how they scale across different clients counts and local training regimes, doing some scenario evaluation. And at the end, I'd have this integration of differential privacy to explore the privacy utility trade-off using compare different aggregation algorithms. Here's a simplified table that shows the performance degradations under fed average. We can see in the regression task, if we consider the baseline, the centralized and ID case, they performed pretty similarly. But once we introduce label skew and feature skew, we see degradation in performance. And then we see similar case in the classification tasks using different partitioners. Okay. So next up, as I said, I want to objectively measure how heterogeneous each partition is. So I compute several statistical metrics to measure, okay, for example, the Wasser stain distance measures the overall shift in the distribution between clients. I've used KL divergence as well, and then as well as the KS test, which gives us a p-value to indicate whether 2 distribution differ significantly. Yep. And then here's a visual counterpart to what we have on the last slides, for example. On panel A, we see kind of what kind of non-IVness is being introduced when we use a continuous partitioner with strictness of 0.5. And then and the number B is how we introduce feature skew and quantity skew when we do the scaffold clustering. And the third one is kind of the PCA visualization in 2D of what if we use continuous partitioner by molecular weight, then in the feature space, how would different clients being seen differently, which is pretty interesting here. And then, so with the non-IDness being quantified, the next step is to test out how different algorithm performs. And I'll have this table on the next slide, which, so in my dissertation, I've documented in detail like how each performed, but since this is a presentation, I'm gonna this is a summary across different partition tasks. We see for regression tasks, scaffold dominates in most feature skew cases, and then FetNova Flit also performed decently. For the multi-assay classification task, FetNova and scaffold alternate as the top performers depending on the class ratio, for example. And then this concludes the part to compare how different aggregation algorithms can help mitigate the non-IDness. Next up is to look at factors besides other than just pure, let's say, performance accuracy, but other issues, for example, the convergence and stability, which kind of illustrates different convergence behavior when I use different uh, aggregation strategies. On the left, we have the feature skew being created here. On the right, we have the label skew being created here. And we could compare to see, okay, how fast are different aggregation algorithms making this convergence be, and how stable are they? Another thing I compared is how these algorithms scale as the number of clients increase. I've tested from 10 clients to 20 clients to 40 clients, which I think as expected, we see the performance generally decline as data become more fragmented. And then in this case, scaffold maintains as the highest R square value and exhibit the least degradations. And then another one is fairness, which is pretty interesting. So does every client benefit equally? So here I assess per client performance distributions over the final 20 rounds of the training, which means um, if I look back on the training process and I evaluate the global model on, let's say, the each of the clients' data, how does the performance differs across different clients? I mean, in the ideal scenario, we want to train a global model that's equally good for every client. So every client can apply this model to their own data sets, and it's being better than they training only on their local models. And then I think if we consider fairness under different non-ID scenarios and ID scenarios, we see scaffold performing better than Fed average. And then as the last step of the evaluations, I evaluated the how differential privacy interacts with these aggregation algorithms. Actually, thanks to Mohammed, when I was doing the project, I've asked several questions to Mohammed, and he was able to help me. So here we applied a server-side DP using adaptive clipping and Gaussian noise, and then to test different privacy budgets. Lower budget absolute means stronger privacy with no noise. And as expected, we see all models degrade with stricter privacy, but I would say the degrees varies. I would say if we can see across all different partitioners, the scaffold feature skew and continuous label skew, the scaffold algorithm consistently achieve the highest utility. In this case, is the lowest loss. And then that's kind of the conclusion for the privacy utility trade-off section. I've also, to verify these differences, aren't just like random verifications, done some statistical tests showing comparing distribution of results across different algorithms. Okay. And then kind of to conclude, here are the lessons learned for the project. First, the conclusion, there's no one-size-fits-all algorithms. So each strategy has its strength for specific data regimes. For example, when we consider extreme imbalance, FatProx might be more superior. FatNova was also superior when we consider moderate skew and scaffold for feature-driven non-IDness. Secondly, I would say the way we split the data matters enormously. Artificial ID partitions can give misleading conclusions, and then chemistry meaningful partitions like the scaffold partitioners I introduced in the property-based splits, they reveal behaviors invisible in the standard benchmark, like historical papers. And then thirdly, the result is scaffold consistently preserve the best performance under the differential privacy scenario. And finally, we need a standardized, reproducible FL evaluation pipeline to enable fair cross-algorithm comparisons and community benchmark, which is the StratoFL framework I introduced. So yep, that's concludes my presentation. Thank you, everyone.
Yeah, wonderful. Very complete piece of work, this one. Very interesting. Let's just see if we've got any questions. But anyone on the call, feel free if you want to ask questions, just go for it, really. There's this one from Slack saying most FL is done on things like Sapphire 10. What did you discover about using this kind of data that was different?
Sorry, could you repeat the question?
The person's asking, they're making a connection to the fact that most of the results out there are based on data sets like Sapphire 10, I guess data sets of that kind, whereas this data set is quite different. So because of that difference, what did you kind of observe? I know you had lessons learned slide, but like what were some things that jumped out to you about how FL is different under this type of data?
Good question, actually. I think when we see those kind of historical experiments with those standardized data sets, I would say those does not match the realistic scenario. And when I do test on realistic scenarios, I would say my lesson learned is that because I think if we consider a lot of other research into the field, they might easily conclude that okay, this aggregation algorithm is the one that's superior under a specific scenario. But I think what I realized after running this experiment is that I would say it's more application specific. And then there's so many different types of non-ID scenarios that you can think of that could appear in the real life settings. So I would say in the actual world when we are actually kind of implementing stuff and actually using the federated learning, and it's better that we consider all sorts of different aggregation algorithms, and we might find one that's kind of most suitable for this specific setting.
Okay, cool. I guess conventional wisdom is things like FedProx does pretty well under non-IDness, and FedAverage does, generally pretty well on many settings. Like it's a pretty, sometimes even a hard baseline to beat, depending on how you evaluate. So I guess you're saying that there's no consistency though. You kind of maybe would you say that kind of consistency that people might have as an intuition is a bit wrong? That
I wouldn't
like
say it's wrong,
really,
actually. Actually, the thing you just mentioned, I think it's correct. I think
that's
which is
correct.
also consistent with my experiments. I think under non-ID settings,
Yeah.
FatProx almost always better than FedAverage in my case.
Yeah,
So I think,
makes sense. Yeah, I wasn't really saying that. I wasn't saying that necessarily is wrong, but I think it's worth verifying
yeah,
because a lot of the data that people do experiments on is pretty far removed from the data that people are actually motivated to do FL in.
Yeah.
So it's interesting. Cool. Let me see what else I can find. This is a simple question. They're asking for this data set, does that correspond well to tasks done in the domain?
I see. So when I was thinking about the actual data sets, I was kind of doing some literature review of stuff or tasks commonly being done in the domain. So I chose these two tasks because I would say these does correspond pretty well to kind of two of the most frequent like research directions or prediction directions. And then the fact I've used ChemBL, which is a website that collects data set from all different like scientific journals, which kind of actually mimics the real world non-IIDness because the data sets on its own, I collected them from different places as well, and then kind of merged them together. So I think it's fairly realistic. Yeah.
Yeah, it's a pretty good job. Great, cool. I don't see anything. Well, those are two good questions I found. So yeah, good stuff. Great. Let's start to wrap this show up. So I just want to conclude saying thank you to everyone who came today. Great stuff. 3 amazing talks, 3 amazing projects. Our next event will be December 3rd. We always schedule these on the first Wednesday of the month. Very casual get together, sharing what some exciting things are happening in the flower community and FL in general. These links on this page are those that you can use to follow up on if you want to join the Slack workspace, interact with some of the teams that you see here and also some of the people behind Flower. Feel free to join. If you're interested in some of the events that we run, such as the ones I mentioned earlier at the start of the event, you can subscribe to the calendar. And you'll always find on our website, at least, the edited versions of this event appear as nicely curated individual talks and also as the whole event by itself. It also appears on our YouTube page. So that's it from me. Thank you everyone for joining. I really appreciate your time and all the great hard work that you put into FL. So thank you all. Take care. Bye-bye.